Hi guys! From this video, I will begin to explain the roll center, which is important in vehicle dynamics. In order to understand the roll center accurately, various basic knowledge is required. This video is the first video, part 1 of the roll center, and I will explain kinematics for understanding roll centers. What I'll explain in this video is sprung mass and unsprung mass, understanding roll center, roll axis, types of roll centers, kinematic modeling for vehicle, and instant centers in kinematics. I have a quiz for you. Which is a right expression for roll center? Number 1. The center of rotation of the sprung mass during the rolling motion of a vehicle. Number 2. It is a point on the vertical cross-section, including the left and right wheel centers, where a lateral force can be applied to the sprung mass without causing suspension roll motion. Number 3. The roll center is a unique value of the vehicle and does not change under any motion state. Please choose one of 3. In order to understand roll center, we need to distinguish between the types of mass in a vehicle. There are 3 types of mass in a vehicle: sprung mass, unsprung mass, and hybrid mass, which connects the sprung mass and unsprung mass. Let's look at each of them in turn. First, let's look at sprung mass. Sprung masses are the masses that move as one unit with the car body on springs. These includes the body, engine, transmission, suspension system, fuel tank, rear differential, and propeller shaft, and so on. A large sprung mass means that the springs and shock absorbers have a lot of mass to handle. The unsprung masses are the parts that move as one unit with the wheel under the spring. These include the hub assembly, the braking system, the tires, and the wheel rim. If the unsprung mass is too large compared to the sprung mass, the road contact performance will be poor and there will be problems with turning, acceleration, and braking. Hybrid masses are the parts that connect sprung mass and unsprung mass. They are a mixture of sprung mass and unsprung mass, with one side moving like sprung mass and the other side moving like unsprung mass. These include upper arms, lower arms, drive shafts, and tie rods. Usually, half of the mass is treated as sprung mass and the other half is treated as unsprung mass. Let's learn about the types of roll centers. There are 3 types of roll centers that have been used so far. They are kinematic roll center, geometric roll center, and force roll center. Even now, the definition of roll center varies depending on the researchers and writers, and there are many cases where it is used incorrectly. When the lateral acceleration is relatively small, these 3 roll centers coincide with each other. Therefore, in this video, I will first explain how to find the roll center when the lateral acceleration is relatively small and the suspension geometry can be treated as not changing, and I will explain the remaining cases where the lateral acceleration is large in the next video. Let's find out the definition and meaning of the roll center. The roll center definition of SAE International is expressed as the roll center is the point in the transverse vertical plane through the wheel centers at which lateral forces may be applied to the sprung mass without producing suspension roll. What we have to know on SAE definition are: roll center is defined using the applied force and the height of the roll center is defined, but there is no mention of its lateral location. The roll center is an important characteristic value that summarizes the important characteristics of the developed suspension. The roll center indicates the location where the lateral force generated from the wheel is transferred to the sprung mass, and therefore it affects the behavior of both the sprung mass and the unsprung mass, so it directly affects cornering. Let's learn about roll centers and roll axis. Roll centers can be found at the front and rear wheels, respectively. First, for the front wheels, it can be found on the cross-section of the vehicle that passes through the centers of the left and right wheels. Similarly, For the rear wheels, it can be found on the cross-section of the vehicle that passes through the centers of the left and right wheels. Therefore, there are two roll centers, one on the front cross-section and one on the rear cross-section. If you connect these two with a straight line, you can get a purple straight line in the fore-aft direction of the vehicle, as shown in the figure, and this is called the roll axis. Let's find out what the roll center means. All recently published vehicle dynamics books commonly point out that the expression roll center is incorrect. When the expression roll center was first used a long time ago, it was borrowed from the expression instant center in kinematics, and it is assumed that the expression roll center was used by removing the instant and replacing it with roll. The reason why this expression is incorrect can be explained as follows. In reality, when a vehicle rolls, it does not rotate around an axis. It also does not rotate around a point. Therefore, if the vehicle is already rolling, it cannot be called a roll center. The roll center is a position defined at a certain moment in the roll motion. Professor Massimo Ghiziani uses the expression no roll center instead of roll center in his book Science for Vehicle Dynamics. However, the expression roll center has been used traditionally in the industry and continues to be used without disappearing. Regardless of the appropriateness of the expression, the roll center is an important characteristic that summarizes the developed suspension. Let's learn how to represent a vehicle kinematically. If we represent the entire vehicle with double A-arm suspension as a kinematic link, it would look like this figure. All parts that move as a whole are represented by a single link. For example, the body includes all the sprung mass systems we have discussed above, namely the body, engine, transmission, fuel tank, propeller shaft, differential, etc. The wheel and tire includes the unsprung mass, namely the tire, wheel rim, brake, and hub assembly. Let's take a look at the links and joints used in kinematics. The figure here shows the links and joints of a vehicle viewed from behind. First, the road surface is represented by a fixed link, which is the non-moving link. It is link 1 in the figure. The entire sprung mass is represented by link 5. The left unsprung mass is link 2, and the right unsprung mass is link 8. Next, there are the links of the hybrid mass. The left upper arm is link 3, and the left lower arm is link 4. Next, the right upper arm is link 6, and the right lower arm is link 7. As shown, a vehicle with double A-arm suspension has 8 links. This time, let's learn about joints. The point where the left wheel meets the road is joint 1. The point where the left wheel meets the left upper arm is joint 2. The point where the left upper arm meets the body is joint 3. The point where the left wheel meets the lower arm is joint 4. The point where the left lower arm meets the body is joint 5. Looking at the right side, the point where the body meets the right upper arm is joint 6. The point where the right upper arm meets the right wheel is joint 7. The point where the body meets the right lower arm is joint 8. The point where the right lower arm meets the right wheel is joint 9. Finally, the point where the right wheel meets the road is joint 10. As shown, the double A-arm suspension has 10 joints. For a clearer understanding, let's look at the types of joints defined in kinematics. Joints are also called pairs. In kinematics, pairs are largely divided into two types, lower pairs and higher pairs. Lower pairs are joints that make surface contact, and higher pairs are joints that make line or point contact. Of course, there are exceptions such as needle bearings, but most can be distinguished by the types of contact. There are 6 basic joint types in lower pairs, and we will look at them one by one. The first lower pair is a revolute joint, which means it can only rotate and not translate. It has 1 degree of freedom. The body, shown in grey, can rotate around the green pin. The second lower pair is a prism joint that cannot rotate and can only translate axially. It has 1 degree of freedom. The body, shown in grey, can translate up and down along the green pin. The third lower pair is a screw joint that can rotate and translate. A screw joint has 1 degree of freedom. This is because when the angle psi is determined, the displacement value delta s is determined accordingly, and conversely, when the displacement value delta s is determined, the angle delta psi is determined accordingly. In other words, the angle delta psi and the displacement delta s are not independent variables, but dependent variables. In a screw joint, a body in grey can translate up and down and rotate along the green screw. The fourth lower pair is a cylinder joint that can rotate and translate. The cylinder joint has 2 degrees of freedom because the angle psi and the displacement delta s can move independently. In other words, the angle delta psi and the displacement delta s are independent variables. In the cylindrical joint, the grey bodies can translate up and down and rotate about the cylinder axis independently without affecting each other along the green pin. The fifth lower pair is a sphere joint that can rotate about 3 axes. The sphere joint has 3 degrees of freedom because the angles psi, phi, and theta can move independently of each other. In other words, the angles delta psi, phi, and theta are independent variables. In the sphere joint, the rigid body, shown in grey, can rotate independently about the x, y, and z axes without affecting each other about the shaded sphere shown in grey body. The sixth lower pair is a flat plane joint that can rotate about 1 axis and translate in all directions in 1 plane. A flat plane joint has 3 degrees of freedom because the angle psi, the displacement x, and the displacement y can all move independently. In other words, the angle delta psi, the displacement x, and the displacement y are independent variables. In a flat plane joint, a rigid body, shown in green, can rotate about an axis perpendicular to a flat plane, shown in grey, and can translate independently about 2 axes in the plane, the x and y axes, without affecting each other. Here is a summary of the 6 lower pairs we have discussed so far. The revolute pair is represented by the capital R. It allows rotation about 1 axis and translation is not possible. It has 1 degree of freedom. The prism pair is represented by the capital P. It allows translation about 1 axis and rotation is not possible. It has 1 degree of freedom. The screw pair is represented by the capital H. It allows rotation about 1 axis and translation is possible, but they are dependent on each other. It has 1 degree of freedom. The cylinder pair is represented by the capital C. It allows rotation about 1 axis and translation is also possible. It has 2 degrees of freedom. The sphere pair is represented by the capital S. It allows rotation about 3 axes and translation is not possible. It has 3 degrees of freedom. The flat pair is represented by the capital F. It allows rotation about a single plane and translation in 2 directions. It has 3 degrees of freedom. You can find this table in the book A Theory of Machines and Mechanisms 5th edition written by John J. Uecker, Jr. The above was a 3-dimensional analysis, and from now on we will look at kinematics on a 2-dimensional plane. Mobility of a mechanism is the degree of freedom of a mechanism. It can be defined as mobility of a mechanism is the degree of freedom, the number of input parameters that must be independently controlled to bring the device into a particular posture, usually the number of joint variables. For a 2-dimensional planar mechanism, the mobility can be calculated as in equation 1. There are exceptions to which equation 1 does not apply, but we will ignore them here. In equation 1, m represents mobility, n represents the total number of links, J1 represents the number of joints with 1 degree of freedom, and J2 represents the number of joints with 2 degrees of freedom. In the example on the left, the number of total links n is 4, the number of joints with 1 degree of freedom is 4, and the number of joints with 2 degrees of freedom is 0. So if we substitute all of these into equation 1, we can obtain the result of equation 3 as the mobility value. The mobility of the mechanism on the left is 1. In the figure, if we control the angle of link 2 or link 4, we can control the posture of the entire mechanism. For reference, the equation for calculating the mobility of a three-dimensional spatial mechanism is as in equation 2. Let's learn more about the concept of mobility with the mechanism examined above. The mobility of the mechanism shown here is 1 as calculated above. When the angle theta of the fixed link 1 and the rotatable link 2 are fixed around the joint I1-2, the posture of the entire mechanism is determined. For example, in the upper figure, if link 2 rotates counterclockwise so that the angle theta of link 2 becomes theta 1, the posture of the entire mechanism is determined, and likewise, in the lower figure, if link 2 rotates clockwise so that the angle theta of link 2 becomes theta 2, the posture of the entire mechanism is also determined. Now that we understand the concept of mobility, let's find the mobility value of the double A-arm suspension we looked at earlier. Referring to the figure, as shown in equation 4, the total number of links n of the double A-arm suspension is 8, the total number of joints J1 with 1 degree of freedom is 10, and the total number of joints J2 with 2 degrees of freedom is 0. If we substitute the conditions of equation 4 into the mobility calculation equation 1 we formulated earlier, we can calculate the mobility value as shown in equation 5, and we can see that the mobility value of the double A-arm suspension is 1. In kinematics, the instantaneous center of velocity can be defined in 2 ways. The first definition uses relative velocities and is as follows: a point in one body about which some other body is rotating either permanently or at the instant. Let's illustrate this with the figure on the left. In the figure on the left, body 1 is the background. Body 2 is shaded in gray. The two bodies are moving in a mixed rotational and translational motion in the plane. An observer is monitoring body 2 from body 1. At any instant of time during this motion, let's say that at one point A of body 2 on the left, the instantaneous velocity has magnitude and direction VA, and at another point B of body 2, the instantaneous velocity has magnitude and direction VB. Since the instantaneous velocity is perpendicular to the radius, if we draw a line perpendicular to the velocities VA and VB from A and B, respectively, they will intersect at a point C in the plane. The point C is the instantaneous center for both bodies A and B. To an observer in body 1, point C of body 2 appears to be motionless instantaneously. Therefore, we can say that point C is the instantaneous center of velocity for body A and body B. If the position of point C changes over time, the positions of a pair of points are instantaneously coincident, and if the positions of point C do not change over time, they are continuously coincident. The second definition of the instant center uses absolute velocity and is as follows: a point common to two bodies having the same linear velocity in both magnitude and direction in each. Let's explain this with the figure on the left. In the figure on the left, the two bodies are moving in a mixed motion of rotation and translation in the plane. Meanwhile, the observer, unlike in the case of the definition of the previous one, is not on body 1, but is observing the absolute velocity of the two bodies in an inertial frame of reference. At any given moment, there is a pair of points that coincide with each other, as shown in the figure, such that the point where the lines drawn perpendicular to the velocity from points A and B of body 1 intersect, and the point where the lines drawn perpendicular to the velocity from points D and E of body 2 intersect are point C. From the observer's perspective, at one moment, point C, a point on body 1 and body 2, appears to coincide in the same position in the plane and move at the same velocity. At this time, point C is the instantaneous rotational center for both bodies 1 and 2. Therefore, we can say that point C is the instantaneous center for bodies 1 and 2. You can find these definitions in the book Kinematics and Dynamics of Machine 2nd edition, written by George H. Martin. If you know the velocity of any 2 points on the body, you can find the instant center. As shown in the figure on the left, if you draw a straight line perpendicular to the direction of velocity of point A and a perpendicular line perpendicular to the direction of velocity of point B, they will meet at a point C on the plane. This point C is the instantaneous center. The instantaneous radius of rotation about point A and the instantaneous radius of rotation about point B may be the same or different. If the body is a rigid one, point C becomes the instantaneous center for all points on the rigid body. If the velocities of 2 points are in the same direction and have different magnitudes, the instantaneous center position C can be obtained by drawing a straight line connecting the ends of the velocity vectors. If the body is a rigid body, point C becomes the instantaneous center for all points on the body. If the magnitude and direction of the velocity at 2 different points are the same, the body is in a translational motion without rotation. In this case, the instantaneous center C of the body is infinitely far away. This is the case when a perfect slide occurs during heavy braking of a vehicle. There are 2 types of instant centers: primary instant centers, which can be found visually, and secondary instant centers, which cannot be found visually and require analytical methods to find. First, let's look at the primary instant centers. Primary instant centers are easy to find visually. All the joints of the links that are connected to each other are primary instant centers. The mechanism on the left has for primary instant centers. They are I12, I23, I34, and I14. I23 and I34, which are shown in red, are moving instant centers, so they are called moving centers, and I12 and I14 are fixed instant centers because they cannot move. Let's take a look at the second type of primary instant center. For a wheel that rolls on the ground without slipping, the primary instant center is the point of contact with the road surface. When determining the instant center in a mechanism that includes the tire and wheel of a vehicle, it is assumed that there is no relative motion between the center of the wheel and the point of contact with the road surface. The third type of primary instant center is when the wheels do not roll and are held in place by the force of the brakes, causing a perfect slip, skidding along the road surface. In this case, the instant center, as we have seen, moves infinitely farther away. The fourth type of primary instant center occurs when the wheel rotation speed increases rapidly, but the wheel torque is not transmitted to the road surface, causing the wheel to spin. When the engine torque is excessively applied, the vehicle does not accelerate and the wheel spins. This occurs when the engine torque is greatly applied on a road surface with low friction. At this time, the tire experiences a perfect slip and spins on the road surface. The instant center in this case is the center of the wheel. Let's learn about the secondary instant center. The location of the secondary instant centers are not directly visible from the mechanism. We must use the Aronhold-Kennedy theorem to find the location of the secondary instant center. Given a mechanism, let's see how many instant centers there are and how to find them using the Aronhold-Kennedy theorem. The Aronhold-Kennedy theorem can be expressed as follows. The 3 instantaneous centers shared by 3 bodies in motion all lie on the same straight line with respect to each other, whether connected or not. The proof of the Aronhold-Kennedy theorem can be done simply without using formulas. It can be proven using the logic that there is no case where 3 instantaneous centers are not on the same straight line. Let's prove the Aronhold-Kennedy theorem. There are three bodies as shown in the figure. For the sake of explanation, we assume that body 1 is fixed. I12 is the instantaneous center where body 2 rotates instantaneously around the point of body 1, and I13 is the instantaneous center where body 3 rotates instantaneously around the point of body 1. The three bodies do not necessarily have to be connected. Let's find the instantaneous center I23 in this state. First, let's assume that point P is the instant center as shown in the figure. The motion that body 2 can perform is to rotate around the instant center I12 with body 1, and the instantaneous radius of rotation at this time is R2. Similarly, the motion that body 3 can perform is to rotate around the instant center I13 with body 1, and the instantaneous radius of rotation is R3. On the other hand, the direction of the velocity is perpendicular to the radius, so the directions of the velocities Vp of body 2 and body 3 are different, as shown in the figure. From the definition of the instant center, the magnitude and direction of the velocities of the instant center must be the same, so point P is not the instant center. Therefore, in order for the direction of the velocity to be perpendicular to R2 and R3 and for the magnitude of the velocity to be the same, I23 must be on the straight line connecting I12 and I13. If they are not on the straight line, as we have seen, the directions of the velocities do not match, and it is not an instant center because it goes against the definition of an instant center. I23 in the figure is on the straight line connecting I12 and I13. The velocity of I23 from body 2 and the velocity of I23 from body 3 are the same in magnitude and direction. Therefore, in the case of the figure, there is only one point, I23, as the instant center. Through the discussion up to this point, the Aronhold-Kennedy theorem has been proven. Let's find out the formula for calculating the total number of instant centers. Since the number of instant centers exists between two different links, it can be calculated using the formula for combinations. In the mechanism of the figure, the total number of links is 4, so if you substitute 4 into equation 6, you can get the answer, and the total number of instant centers is 6. Kennedy circle is a great help in determining the number of instant centers and finding the location of instant centers. Let's learn how to draw a Kennedy circle. First, draw a circle as shown on the right and mark points at roughly equal intervals equal to the number of links. In this example, there are 4 links, so we mark for points east, west, south, and north. Next, connect the nearby points. The straight line connecting link 1 and link 2 represents instant center I12. The straight line connecting link 2 and link 3 represents instant center I23. The straight line connecting link 3 and link 4 represents instant center I34. The straight line connecting link 4 and link 1 represents instant center I14. So far, we have marked for primary instant centers. Since there are 6 instant centers in total, we need to find 2 more secondary instant centers. Secondary instant centers of Kennedy circle can be found by connecting the links that are not yet connected. First, connect link 1 and link 3 with a dotted line and mark it as instant center I13. Next, connect link 2 and link 4 and mark it as I24. With this, we have found 2 more secondary instant centers. Next, we will explain how to find 2 more secondary instant centers using Kennedy circle. First, let's find the secondary instant center I24. According to the Aronhold-Kennedy theorem, the 3 instant centers shared by 3 moving bodies are all in the same straight line with respect to each other. In the Kennedy circle, the 3 links and the 3 instant centers are represented by triangles. In the right figure, the triangle containing link 1, link 2, and link 4 can be represented in yellow. The red dashed line represents the secondary instant center I24. What the yellow triangle means is that the secondary instant center I24 must be in a straight line with the primary instant centers I12 and I14. Therefore, we draw a long line through I12 and I14 on the left mechanism. We know that the secondary instant center I24 is on this straight line, but we don't know exactly where it is. Continuing to refer to the remaining neighboring triangles. The remaining triangles, including link 2, link 3, and link 4, are shown in yellow in the right figure. The red dashed line represents the secondary instant center I24 as before. What the yellow triangle means is that the secondary instant center I24 must be on a straight line with the primary instant centers I23 and I34. Therefore, draw a long line through I23 and I34 on the left mechanism. The line drawn here intersects the line drawn earlier through I12 and I14, and the point where they intersect is the secondary instant center I24. Now that we have found the secondary instant center I24, we change the red dashed line of I24 to a solid black line so that we do not have to repeat the same task. It is a good idea to organize them as you complete them one by one, as multiple secondary instant centers can be confusing. Second, let's find the secondary instant center I13. Similarly, according to the Aronhold-Kennedy theorem, the three instant centers shared by three moving bodies are all on the same straight line. In the Kennedy circle, the three links and the three instant centers are represented by triangles. In the right figure, the triangle containing link 1, link 2, and link 3 can be represented in yellow. The green dashed line represents the secondary instant center I13. What the yellow triangle means is that the secondary instant center I13 must be on a straight line with the primary instant centers I12 and I23. Therefore, we draw a long line through I12 and I23 on the left mechanism. We know that the secondary instant center I13 is on this line, but we don't know exactly where it is. Continuing to refer to the remaining neighboring triangles. The remaining triangles, including link 1, link 3, and link 4, are shown in yellow in the right figure. The green dashed line represents the secondary instant center I13 as before. What the yellow triangle means is that the secondary instant center I24 must be on a straight line with the primary instant centers I14 and I34. Therefore, draw a long line through I14 and I34 on the left mechanism. The line drawn here intersects the line drawn through I12 and I23 drawn earlier, and the point where they intersect is the secondary instant center I13. Now that we have found the secondary instant center I13, we change the green dashed line of I13 to a black solid line so that we do not have to repeat the same task. It is a good idea to organize them as you complete each one, as multiple secondary instant centers can be confusing. Here is a summary of how to find the secondary instant center I24 using the Aronhold-Kennedy theorem and Kennedy circle. The three links 1, 2, and 4 have three instant centers, and the three instant centers they share I12, I14, and I24 must be in a straight line. In addition, the three instant centers I23, I34, and I24 shared by the other three links 2, 3, and 4 must also be in a straight line. Therefore, we can find point I24 that satisfies condition 1 and 2 above. Here is a summary of how to find the secondary instant center I13 using the Aronhold-Kennedy theorem and Kennedy circle. The three links 1, 2, and 3 have three instant centers, and the three instant centers they share I12, I23, and I13 must be in a straight line. In addition, the three instant centers I34, I14, and I13 shared by the other three links 3, 4, and 1 must also be on a straight line. Therefore, we can find point I13 that satisfies condition 1 and 2 above. Let's find the answer to the quiz. Which of the following correctly describes the roll center? First, the roll center is not the center around which the sprung mass rotates during the vehicle's roll motion. Second, it is a point on the vertical cross-section including the left and right wheel centers where a lateral force can be applied to the sprung mass without causing suspension roll motion. This is the right answer to the quiz. Third, the roll center is not an inherent property of the vehicle, but is a value that continuously changes during the vehicle's roll motion. Let's summarize this video. There are three types of vehicle masses: sprung mass, unsprung mass, hybrid mass. What we have to know about roll center are, in reality, when a vehicle rolls, it does not rotate around one axis. The roll center is a position defined at a certain moment in the roll motion. Aside from the appropriateness of the expression, the roll center is an important characteristic that summarizes the developed suspension. I explained kinematics for roll center. Two types of joints or pairs: lower pair, higher pair. Lower pair is surface contact, higher pair is line contact or point contact. There are 6 basic joint types for lower pairs. Double A-arm suspension has 8 links and 10 lower pairs. Instant centers can be defined in 2 ways. First, a point in one body about which some other body is rotating either permanently or at the instant. Second, a point common to 2 bodies having the same linear velocity in both magnitude and direction in each. There are 2 types of instant centers. Primary instant centers can be found visually because they are joints of links connecting each other. Secondary instant centers cannot be found visually and is found using analytical methods. To find secondary instant centers, the Aronhold-Kennedy theorem should be used, which states that the 3 instant centers shared by 3 moving bodies are all on the same straight line whether connected or not. Using Kennedy circles, it is very helpful to determine the number of instant centers and to find the locations of instant centers. If you watch the previous videos, you can learn about various fields of automotive knowledge and enjoy a more in-depth understanding of future videos. In the last video, E0069, the third part of curve fitting using the least square method, how to linearize a non-linear function using the Taylor series, apply the least square method, and then perform curve fitting through repeated calculations. In addition, application methods have been explained with examples of exponential functions and Fourier functions. The recent video H0068 is the 4th part of curve fitting using the least square method. It explains a method for more accurate curve fitting by assigning importance to data using a weight function in the least squares method. The next video will explain vehicle roll centers of various vehicle suspension types. Please hit the thumbs up and catch the brand new videos by free subscription. So what are you waiting for? See you at next videos. Goodbye, guys.